All right, we got a work in progress here, ladies and gentlemen. I think we have what we need to see. We're doing experiment 8B today. It's a Fischer esterification to make isoamyl acetate. So we gotta know how that works. So like I was saying earlier, before we had the idea to start a video, in organic chemistry, when you're studying reactions, you have to know the players in the game. We learned 8 functional groups in 241, and my 242 students will attest to you, more functional groups are coming, especially after they see chapter 19, where that list is going to double. But right now, 8 functional groups. That's not a tough play to learn the players in the play, like a Shakespeare play with only 8 characters. There's no Shakespeare play with that few characters. Okay? And you have to know how they behave and what they do. So today we're talking about carboxylic acid reacting with alcohols to make carboxylic esters and water. 2 molecules coming together to make a larger molecule while at the same time losing water. We call that condensation. If you're a biologist, you might call it dehydration synthesis, aka dehydration synthesis. There you go. Sorry, a lot of my back on that one. It's going to be on a video, we hope. Is it bad news? No. Should have fixed my hair, I know. Yeah. There you go. Here we are. We're making an ester and water. It's a synthesis reaction, isn't it? We like it. And it's also this kind of reaction. And what is that? Not a one-way reaction, but it goes back and forth, which means we can manipulate it. Oh yeah, that's exciting. That's where the money's at. For those who know how to manipulate an equilibrium reaction and make it go the direction you want. Today, it's all about making this ester. This ester right there. Now, on your midterm, you have to be able to go from the name of an ester, from the name of the ester, and tell me which alcohol to use and which carboxylic acid. And I'm going to just break down isoamyl acetate from the ester's name to tell you what alcohol and carboxylic acid you need to, in this case, plan on buying for your midterm. Yeah, that's the next video. So isoamyl acetate, always start at the end. Acetate comes from, now you added the chemicals before we started this lecture. What part provided the acetate in the name? Acetic acid. So when we do our video, and we're supposed to do, well, let's just do this as part of this video. On our scale up exercise, we're supposed to make isobutyl myristate. So we're doing this example right now, isoamyl acetate. Acetate comes from acetic acid, and isoamyl comes from, let's do that in a different color. Isoamyl comes from, what was the name of the alcohol we added into that reaction today? Okay, I'm going to do it this way. Isoamyl alcohol. And a little knowledge about amyl, it's an old name. And it just means pentyl. You might want to learn that because a lot of pharmaceutical agents have amyl in its name. And if you remember that's pentyl, that's going to help you remember something about that pharmaceutical agent. So One of the students correctly pointed out it's called isopentyl alcohol. Now on the midterm, I don't expect you to know that historical fact like the one we're about to do as a practice exercise. This was to make isoamyl, I don't know if that's on the video. Oh, it is. Isoamyl acetate. Acetate comes from acetic acid. Isoamyl comes from isoamyl alcohol. So on our scale up exercise for next midterm, it says isobutyl myristate. So I'll do that down here. Is that on the screen? No. We're at our limit. Isobutyl myristate. So what was the acid and what was the alcohol? And I'm going to try to do this, but wish me luck. There. Myristic acid. Nice. So myristic acid was used and isobutyl alcohol. Isobutyl, oh, it's tight. Okay, so that's for our next video. But we're just going to briefly talk about our experimental conditions today and how we're making it go forward. We got a couple things in our favor today. One, we're going to use Le Chatelier's principle a couple ways. And do you remember what Le Chatelier's principle says about equilibria? It's where the money's at. Trust me. The chemists that know how to manipulate Le Chatelier's principles are the ones that can do very well in life. The medical researchers that know how to exploit Le Chatelier's principle can help a great many people with drug discovery. It's a very important concept. So what are we doing to push equilibrium that way today? We're removing water that's being made as it's being made. What agent are we using for that? Oh, what a coincidence. Our notes from setting up for our experiment had the word silica gel there. Silica gel makes a hydrate with water. That means it converts the water from its liquid form into a complex where it's glued to silica gel, and now it's a solid. Solids are no longer part of the equilibrium. They're invisible to this reaction. That means you've removed water from the equilibrium. Le Chatelier says, what's going to happen to compensate? You're removing a product, you're going to make more products. More ester is the important one, right? That was method one to achieve a higher yield of ester today. Method two is about the millimoles. So we can put them here. How many millimoles of acetic acid are we using today in your data table? 26.2 millimoles. How many millimoles of isopentyl alcohol? It's less, isn't it? 7.4. What does Le Chatelier say about using an excess of one of the reactants? It also pushes the equilibrium to the right.
Is the reactant more excess to the right?
Anytime you add an excess of one of the reactants, you will push equilibrium away from that, which is creating more products. So I got two things pushing to the right. I also have a preventative measure to keep moisture that's in the air from entering the reaction. That would be bad too, wouldn't it? Because if you let water from the air enter, you've added water. What's going to happen to the equilibrium? We don't want that shift, do we? So the the drying tube, prevents moisture from entering into the flask. So it doesn't push the equilibrium back to reactant. All right. Wow, look at that technology there. Let's see. Have we talked about enough stuff? Yeah, drying. So we got that. Preventative measure, silica gel, and excess chemical here. Now, the last discussion for this video, short little video. Why do you think they chose acetic acid to be the excess reactant? Keeping in mind this fact, acetic acid is easy to get rid of based on experiments we've done previously. Excess reactants, you're going to have to get rid of the excess, right? They're lying around at the end. So you want to pick the one that's easier to get rid of the excess, right? Why is it easy to get rid of excess acetic acid from a reaction where you're making a pretty non-polar or organic ester? We separated chemicals the last 2 weeks. We did. Some of them were acid. How did you make the acid water soluble so it didn't want to go with the organic layer? Because our organic layer is going to have our ester today, and we're going to add a water layer when this reaction's over. But that water layer better have something in it to make the acid more water soluble. That was the whole point of the last 2 weeks, by the way. What can you do to an acid to make it more water soluble? This is the third time I've asked it. That's probably a bit of a fib. It's the third day I've asked it. I've asked it multiple times on the other 2 days. It changes the polarity if you add what to an acid? What typically reacts with an acid? A base. We used bicarbonate 1 week. Then the next week we used hydroxide. Both accomplish the same thing. They take the proton off the acid, make it water soluble. Now you can remove it from your ester. You got 2 layers. The ester is going to stay organic. You can't make the ester water soluble. That's good. Stays organic. Okay, so later we're going to extract the reaction mixture when the reaction's all over. This has nothing to do with the reaction, what we're talking about. I want that to be clear. If you're adding bicarbonate during the reaction, you're starting over because you just ruined your catalyst. Think about it. You don't have a catalyst if you've added a base to this reaction. So the reaction is all done. Now it's time to clean up to get rid of the excess reactant. You're going to extract the whole mixture with bicarbonate. We know 3 times is better than 2 is better than 1. We learned that with our email assignment, right? Okay. So I think we're good with this video. And you sure want to stop recording into the cloud? Yes.